This is 7-3's homework in the textbook, starting with number 1. So we are going to give growth factors for the quantities given. Growth factor is the number that we multiply by in our equations that either makes our number go up or go down. So if we're multiplying by a number that is less than 1, like 0.25, that's going to make it go down. And if we multiply by a number greater than 1, like 1.25, that's going to make it go up and grow and increase. So we got to keep that in mind here. So on question number 1, we want to write the growth factor for something that's decreasing. So we have to have a number that's less than 1 exponentially by 17%. So the wrong answer here would be 0.17. 17% is what it's going down by, but if you just multiply by 0.17, 17%, you are finding 17% of it, not going down 17%. If you think about it, you've got 100%, and we just take a little slice of it, 17%. What's the other piece right here? That's 83%. So we got to think about these two numbers together. Those are the two magic numbers because they add up to 100. If I just find 17%, I take 100 and I find 17%, I've taken 83% off, which is different. Okay, we want to just decrease by 17%. So we want to take 17% off of the 100, which means we're going to be left with 83%. And that's the number that we need right here. So we want to multiply by 0.83. Number 2, if we're going to increase, so this is going to be a number more than 100%. Everything's based on your 100%. So when we're decreasing, we're taking 100 and then going down a certain amount. So we went down 17%. So we're left with a growth factor of 83%. When we increase, we're taking our 100 and then we're adding on to it. Okay, we're adding 2.5%. So 2.5% on its own, if we express that as a decimal, is 0.025. Move that decimal 2 spots. And so since we're increasing, we are going to go over 100%. So it's 1.025. Question number 3. We multiply by the growth factor and the quantity does not change. Think about the number you would multiply by where things don't change. That's 1, not 0. That would create a change. 1, when you multiply by it, is not going to change. Okay, number 4. Many teachers have policies about late work that lowers a student's grade for each day that it's late. Suppose a teacher lowers the grade of a 50-point assignment by 20% for every day that it is late. So letter A, let X equal the number of days the assignment is late, and Y the number of points that the assignment would earn. So we're going to make a table. We're going X values all the way from 0 to 5. So on your first day, it's going to be worth 50 points. You handed it on time. Now, if you're 1 day late, it's going down 20%. So if you're at 100% and it goes down 20%, you're not getting a 20%. Think about how unfair that would be. So 100% on your first day, you don't get a 20% on your next day. 20% comes off, which means you can still earn 80% of the grade. Only 20% is coming off. So we need to take 50 and multiply it by 80%. And now these are actually going to be our exponents. So if you did it to the 0, anything to the 0 is 1. So 50 times 1 is 50. If you do it to the 1, it's just itself. So it's going to be 50 times 0.8, and that's 40. So after 1 day, it's now worth 40 points. So it went down 80%. It's going to go down another 80%. So you could do two different things here. You could take the 40, that's what it's worth now, and lower that 20%. So now it's 0.8. Okay, so it's 32. The other way you could have got there is you could go ahead and take this exponent and throw it in up here. So 50 times 0.8 raised to the second. And you'll see you're also going to get 32. So two different ways to think about it. You can go one step at a time, multiplying by 0.8, taking 80%, okay, which is decreasing it by 20%, or just keep plugging in that exponent. So we're going to do 50 times 0.8 raised to the third, which is 25.6. We're going to do it again, but raised to the fourth, 20.48. And one more time. And it's now worth 16.384. Again, you could have just taken each number individually and kept multiplying by 0.8, and that will get you there, or use the initial equation, which will get us all the way there. So B, it says, write the equation that represents the relationship. We've already got it right here. It's 50 times 0.8. I'm going to put it in parentheses just to separate here, and it's raised to the number of days late. Now they said they want an equation, so we'll write equals y. Make sure that we've got an equation. So number 5, suppose a new car cost $32,000 in 2006. We're going to find the value of the car in 1 year if the following is true. So letter A, find the value of the car if it is now worth 85% of its purchase price. So it's worth 85%. So we want to find 85%. We're not taking 85% off. It's worth 85%. So what is 85% of 32,000? So we're going to take 32,000 and we are going to multiply it by 85%, 0.85. And it is worth $27,200. Part B now asks the question differently. The car depreciated, went down 20% of its value. So it's not now worth 20%. It depreciated 20%. So these two, A and B, are specifically worded differently so you can see the difference. Letter A says it's now worth 85%. So if I reworded this first one, I would say that this car depreciated 15%. 100% is the original cost. Down 15% means it's now worth 85%. So two different ways to word this. Worth 85% or depreciated 15%. So here where they say depreciated 20%, you could say it's now worth 80%. It was 100%, goes down or depreciates 20%. It's now worth 80%. So I'm going to take my 32,000 and I'm not going to multiply it by 0.20 because now it's worth 20% if you do that. I'm going to multiply by 0.80 because that's what it's worth now. After it depreciates 20%, it's worth 80%, and it's 25,600. Now let's just say for a second you did multiply 32,000 by 0.20. Okay, you're going to get 6,400. And let's think about what that number means. That's 20% of the 32,000. That's not what it's worth now. It's not worth 20% of what it used to be. It depreciated 20%. It means it went down 20%, which is 6,400. So if I took 32,000 and I make it go down in price by 6,400, that's the 20% that it came down. And when I subtract those, this is what I'm going to get. Because I'm taking 100% and I'm subtracting 20%, which means I'm left with 80%. So the new price is 80% of what it used to be. It depreciated, it went down 20%. Okay, number 6. So we've got a new piece of machinery and it is going to cost $2,470,000. It's depreciating, so going down in value 12% per year. So it's not going to be worth 12% of what it was. That would be a massive drop. It's going down by 12%. So if I take 100% and I depreciate it, go down by 12% each year, that means it's now worth 88% of what it used to be. So that's the number I'm going to need to use here. So find the value of the machine after 15 years. And then letter B, find the value of the machine after t years. So basically write the equation. So I'm going to actually do these backwards. Here's A, and then I'll do B right here. I think it's easier to actually start with B. Let's write the equation. So we're going to take the original price, and every single year it drops by 12%. Okay, so it's now worth 88% of what it used to be based on the number of years, which they say they want us to represent with t. So I'm going to put my t up there. So for letter A now, I'm going to go back and actually do this. So times 0.88 for 15 years. So put that 15 in there and let the calculator do the rest. Three, 6, 3, 0, 2, 5 point 41, 42, depending on how you want to round that. But this is what it's worth now. Okay, so you can see it started out over $2 million, and in 15 years, losing 12% per year, it's only worth $363,000. So over time, that's a big drop. In 1 year, it wouldn't be that big. If you said 2,470,000 times 0.88 raised to the first, so just 0.88. Okay, it's still going to be worth over $2 million after 1 year. So it didn't drop down drastically in the first year. It was worth $2,470,000. Now it's worth $2,173,000 after 1 year. But this is exponential decay. So as time goes, it's going to drop faster and faster and faster here. So after 15 years, it's already down to $363,000. So number 7. Person with diabetes requires a dose of 15 units of insulin. That's what we're starting with here. And assume that 3%. So first of all, let's make sure we get that part right. 3% is 0.03. Okay, and that is what's being lost. It's coming off. So if you take 3% off, you are left with 97% of what you used to have, which is 0.97. So we need to keep all those numbers straight. We are starting with 15. So first of all, we've got two different answers here. We want to write this in an equation with x, and then we're going to actually plug in 30. So I'm going to do these backwards. After x minutes, we are taking 15. It's going down 3%. So that means you're going to be left with 97% of what it was for every minute, and we're using x for minutes here. So how much insulin is in the bloodstream after 30 minutes? So 15 times 0.97 raised to 30. And we're just going to round that off and say about 6. About 6 units. Okay, number 8. Complete the table for the exponential decay situation. So we're going to copy that table. We're starting at 160, and we are going down by 0.75. So it's worth 75% of what it used to be. You could set up this equation, and that's what they want us to do in part B, so we might as well do that right now. So we are starting with 160, and we are taking 75% of it, every single value of x. So there's our equation. So if you wanted to, you could just plug straight in here and put the 1 in, and the 2 in, and the 3 in for each one. But what we're actually doing is taking 25% off every single time, because it's now worth 75% of what it used to be. Now it's worth 75% of what it just was. That's taking 25% off each time. So we're going to have 160 times 0.75. It's 120. Now we're going to have 120 times 0.75, and that's 90. And now 90 times 0.75 equals 67.5. So you can go one at a time multiplying by 0.75, but we also could have used this equation, 160 times 0.75 raised to the first. There's my 120. 160 times 0.75 raised to the second. There's my 90. Or 160 times 0.75 raised to the third. And there's my 67.5. So you can go one at a time, just multiplying by 0.75 each number, or use the equation to jump directly to any of those values. Okay, number 9, we don't have to fill these charts in. We're just classifying the pattern as growth, decay, or constant. So the only way it's constant is if you're multiplying by 1. It's not changing. If you're multiplying by a number less than 1, like, we got to be careful here. When I first looked at this looks like 0.1, but you can look at the other ones, it's times, and then here's the decimal, times, and here's the decimal. So this is multiplying by 1 times 1. That's going to be no change. Okay, this is constant. So number 9 is constant. If you filled that chart in, it would be 35 and 35. You're multiplying by 1. It's a little confusing, looks like 0.1. Okay, number 10. If we're multiplying by 1.13, you're multiplying by any number greater than 1, we're increasing it. Okay, you'd be increasing this by 13%. It would go up by 13%, up by 13%. That is growth. And 11, we're multiplying by a number less than 1. That's going to make it smaller. It's now 32% of the size that it used to be. Now it's 32% of that. That is decay. That is going down. Number 12, fill in the blank. So instead of expressing these in decimals, we're going to look at them as fractions. That's all. So letter A, 2/3 can be the growth factor in an exponential blank, decay or growth. So 2/3, think about your decimals, is less than 1. That's like 0.32, less than 1. So that means this is decay. It's going to make the number go down. And 3/2 will be the growth factor in an exponential blank situation. 3/2, that is more than 1. If you actually put it in your calculator and divide it, 3/2, 3 divided by 2 is 1.5. So that's our growth factor, is 1.5, where before, when it was 2/3, our growth factor is 0.6 repeated. So this is greater than 1. If you're multiplying by anything greater than 1, 1 point something, even if it was 2 point something, 3 point something, that's possible. It's not always 1 point something. Okay, but it's more than 1, which is going to make it grow. Okay, so letter B here is growth. All right, 13. School has 2,500 students, and the number of students is decreasing by 2%. It's going down by 2%. So you don't drastically go from 100% to 2%. Okay, it's going down 2%, which means it's 98% of what it was. So I'm going to put X as my number of years. So this is letter A already here. I was just building it as I read it. Starting with 2,500 students, if it decreases 2% each year, it's now 98% of what it was each year. So based on the number of years, that's letter A. So letter B, we're going to look at it 10 years from now. So 2,500 times 0.98 raised to the 10th. And 2,042 students, 2,043, depending on how you want to look at it. So we'll say about 2,042 students. And if you said 2,043, because you rounded it up, that's fine too. All right, last question. So 15, suppose one plate of tinted glass only allows 60% of light to pass through. Think of stained glass here in the picture. Okay, it's only letting 60% of that light pass through it. So the amount of light, which we're going to represent with y, that will pass through x panes. So how many of these panes do you stack up? The first one you stack up only allows 60% of light to come through. You put another one on it, back to back, and now it's after the light passes through the first one, now it's only letting another 60% go through, and then another 60% if you keep stacking these panes. And they're going to be described by this equation, y equals 0.6 for 60%, raised to the x, which again represents the number of panes that you've stacked up. So letter A, they want us to plot and label 5 points on a graph of this equation. So first of all, I'm going to make a quick XY chart, and then I will graph it. So I'm going to do 0 panes, 1 pane, 2 pane, 3, 4, because that's going to give me 5 points. I don't have to go to 5, it just says 5 points. So if I put 0 in here, got to be careful. If I put 0 in here, that is 1. Anything raised to the 0 is 1. Because think about it in the actual situation. If you put 0 of these panes of glass up, how much light is coming through? That's 1. 100%. Right? 1 represents 100%. 100% is coming through. If I put in 1 here, 0.6 raised to the first is just 0.6. So if I put 1 pane of glass up, 60% of the light is coming through. Now when I put 2 panes up, okay, now I'm getting 60% of 60%. So you can go back to the original equation, 0.6 raised to the second. It's going to be 0.36. But what's actually happening is I took 0.6 where I was at, and then I took 60% of that. So what I'm doing is multiplying each one by 0.6. So if I was going one at a time, you just take each one and multiply by 0.6. So I would take 0.36 times it by 0.6. 60% of 0.36 is going to be 0.216. But the other way you could have got there was to use your equation right here. So you could have done 0.6 raised to the third, which is also going to get you the same answer. So we're doing 0.6 raised to the fourth, and that was 0.1296. Now I haven't actually answered the question. It says plot 5 points on a graph. So I got to do that right here. So my x values are going to go across the bottom. And a good graph is labeled. So what do these numbers represent? These are the number of panes of glass. Okay, and this is the amount of light. And this is like 100%, so that's going to be 1. And we're going to keep getting smaller and smaller, 0.6, 0.3, 0.2, 0.1. So I want to count by 0.1s. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 0.1, 0.2, 0.3, on and on. 0.9, and then 100%. So let's plot these points. At 0, it should be all the way up at 1. Put 1 pane of glass up, it's at 0.6. Put 2 panes of glass, it's at 0.36. 3 panes, it's at 0.21. 4 panes, 0.1. So you can see this is coming down. Now you wouldn't necessarily connect these, but I just want to show you what this looks like. This is a curve, right? It is not a straight line. It drops drastically, it drops a little less, drops a little less, drops a little less, and it's going to bottom out here. So that's question A we've done. Question B now, though, this is the important one. If you put up enough panes of glass, will the amount of light passing through the panes ever be 0 according to the model? So I can put bigger number, bigger number, bigger number. Let's say I put 100 panes of glass up. 0.6 raised to the 100. The calculator doesn't even like how small this number is. 0.6 raised to 50. Calculator doesn't even like that. 0.6 raised to 20. Calculator doesn't even like that. So that's how small these numbers are, but they are not 0. Okay, they're just getting super, super, super small. So 0.6 raised 10 panes of glass. Okay, calculator was able to give us a number. This is more than 0, but very, very small, and it's going to get infinitely smaller and smaller and smaller. But to answer the question, will this ever hit 0? The answer is no, but it will get infinitely smaller and closer to 0, but never hit 0. So there will always be some little form of light getting through. It may be so small that it's unnoticeable to the human eye, but there will always be some small piece of light getting through.